So here with me is Sam Savage, the best-selling author, the founder of probabilitymanagement.org, the developer of the risk analysis add-in for Excel, ChanceCalc, and the lecturer at Stanford University. And here today we are going to get in touch with some of the wisdom of Sam. Thank you, Sam.
Oh,
The scene is
thank you.
yours.
Now, I forget how I was introduced to SimDec. You reached out to me, and when I saw what you people were doing, I saw an immediate need. And I'll give you an example of that. Let's move quickly into it. This involved, well, of course, what do we do? What we do at probabilitymanagement.org is easy to explain. The hard part is getting anyone to understand it. In effect, we have developed the Hindu Arabic numerals of uncertainty. So I'd like to frame this in the context, in a context in which I think both SimDec and our own open standard for communicating uncertainty, which is SIPmath, I want to put these into the same context. And this shows why they just fit together like hand and glove. So I want to talk about stochastic data, the gateway to AI. And we are both up to our ears in this stuff. All right? So before I tell you what stochastic data is, I want to tell you what it does. So the first thing it does is it cures the flaw of averages. The reason we're doing this in the first place is using single numbers leads to horrible errors. You know, so the poster child for the flaw of averages is the statistician who drowns in the river that is on average 3 feet. And the boss comes in, how deep is the river? And you say it varies. And the boss says, give me a number. And you say it's 3 feet on average, and the rest is history. So what do we do to combat the flaw of averages? We simulate. And what probabilitymanagement.org has done is, in effect, create the Hindu Arabic numerals of uncertainty, which are vectors of Monte Carlo realizations. And I'll demonstrate this more in a sec. The next thing it does is these vectors now are the Lego blocks of risk management, among other things. And by Lego blocks, think of the word modularity, as in Hindu Arabic numerals are modular. If you imagine, before Hindu Arabic numerals, you've counted up a pile of beans. There are 2,000 beans. And someone walks in the room with another bean, and they put it down next to the first one. How many are there now? Oh, no, now we have to count the whole pile again. Right? With simulation, that's the way it is. Oh, we simulated our risk. Oh, you came in with a new risk? We have to run another 8-hour simulation. No. We add what we call the SIP to the new simulation. It's like adding a new bean instead of recounting. Okay? So big simulation models are often, they're non-modular, like sandcastles. They collapse under their own weight. The SIPs are these modules that can be snapped together. They are vectors, and I'll demonstrate that in a second. The last thing that really is so important here is that stochastic data enables what I call chanceification. So simulation is wonderful. I'm addicted to it. Simulating uncertainty, it's been around for a long time. But there are some big barriers. Number one, you need simulation software. Oh, not anymore. Now it works in native Excel. The other barrier, most people have no idea how to generate the appropriate random variables. And what chanceification is about is that most people don't know how to generate electricity, so they let other people do it for them. There's something called the power grid, and we have what I call the probability power grid, in which over here, that's probably AI. The key is what kind of information is going over the power grid to reach your light bulb. And we have developed standards in that area. So I'm going to show you the first application of probability management at Royal Dutch Shell. And the definition of probability management is storing and retrieving and calculating with stochastic data. So if I were looking at the uncertainty of rolling a die, the boss says, what's the number going to be? And you say it's uncertain. The boss says, well, give me a number. Well, on average, it's 3.5. So we have these lovely flat dice. On average, it's 3.5. And so that's what you give the boss. We want the boss to know there's a crapshoot going on. And you cannot play craps with these. You cannot practice for a crap game with these. We store 10,000 die rolls. And the 10,000 die rolls are, I think, the easiest way to understand what we do. I'm just going to pop this up here behind me on my green screen. So I have 3 dice. Now, this is native Excel. This is very important. Okay? It's native Excel. And I have 3 SIPs down here. A SIP is a vector, in this case, of 10,000 Monte Carlo trials of rolling a die. Why SIP? Because I needed words that sounded like bit and byte so they'd fit into your brain. You already got receptacles for those. So SIP and slurp sound a lot like bit and byte. SIP is stochastic information packet. Sure, we're talking about stochastic data. Slurp is stochastic library unit with relationships preserved. And so these things go down 10,000 times. Now, in native Excel, we have what's known as an index statement. It just points into the array, and it points into it based on an index. So roll 1 was a 4, a 6, and a 5. Roll 9,765 was 3 1s. Oops, did the wrong number. There it goes, 3 1s. And so it's auditable data. And that is very important because when it comes to simulation, the accountants don't like randomness. All right, now what I'm going to do is that we're looking at a single die, and the number 1, I've got many other files open, so this is a little slower than it is normally. But I'm looking at a single die, and let's see what happens when we add 2 dice together. That was 10,000 die rolls in native Excel. Of course, there are more 7s than anything else because there's this thing called the central limit theorem somewhere. And what's going on is that the data table command in Excel, the data table function, which you'll never figure out how to use without watching YouTube, it is running the numbers 1 through 10,000 through that cell while recalculating this cell. Now, I want to point out, Hindu Arabic numerals were no easy sell. And in 1199, when Fibonacci brought them to Italy, he said, I have this great new way to communicate and calculate with numbers. And most people said, what the heck is a number? But the money changers and the accountants and those folks said, can't you see, we're busy. We have only 6 days to add up this column of Roman numerals. And Fibonacci said, but my way is so much faster. And they said, get out of town. We bill by the hour, right? That was 1199. He brought them in. In 1500, they were still trying to outlaw Hindu Arabic numerals in Florence. I swear to God. But ultimately, they made them through. They're very good. It ushered in a new era of thought. And we believe that SIPs, the Hindu-Arabic numerals of uncertainty, usher in a new era of thought. And by the way, we call it SIPmath. And SIPmath and SimDec are like siblings, as you're about to see. But I want to define the new era of thought. And so it is called the chance age. I want to define for you now the chance age. This is an extremely bombastic concept. And I've learned that if one is to be bombastic, you need receipts. So I'm the father of the chance age. And here's the receipt. It's from GoDaddy. Dear Sam, thanks for your order. chanceage.com was $12.17. That's chanceage.org down there for $10.17. That was at a time when Bronze Age, by the way, was selling for $50,000. So just wanted to establish that. But then what is the chance age? So in the chance age, when the boss says, give me a number, you say, what do you want it to be, boss? Here are your chances. Okay? So we're multiplying two dice, or we added two dice together, and then for some reason, we need to multiply them. So one die represents quantity of an item sold. The other one is price per unit, which is uncertain. We multiply them together, we get some wacky looking thing over here. And the boss says, what's the number going to be? And you say, what do you want it to be, boss? Okay? And so the boss says, well, it's got to be greater than 8. Greater than 8, please, or we're in big trouble. And you say 55.6%. And how do you know that? It's the count if statement. We're just counting the number of times on the output SIP that it's greater than 8. So two concepts for the chance age. And you're there. Vectors of uncertainties. Here they are. You do arithmetic with the vectors. It's called vector arithmetic. How about that? There are even things called vector databases these days. All of AI is built around this stuff. So this was the application I told you about at Royal Dutch Shell. It was back in 2005, and this was before native Excel could do this. This model is extremely cumbersome in that this is the real model. This is a teaching model I used at Cambridge University to teach Shell execs about this, because there is education to get people into the chance age. So in this model, imagine taking an Excel model that looked like something and contorting it into a single row, then copying it down so every row looked at a different row of what we're going to call the slurp. Now the slurp is a bunch of vectors, a stochastic library unit with relationships preserved. Preserved through what? Oh, the price of oil. When oil price goes up, all the oil wells are doing better. When gas price in Europe goes up, all the European gas prices, all the European gas projects go up, okay? So if we look at this, let me show you the various components here. So we have the projects listed down at the bottom, and this was a make-believe thing to get the Shell execs to think portfolio-wise. And basically we have Nigeria and Nigeria 2 as the two highest average profit exploration projects, right? This is modern portfolio theory applied to portfolio assets, to petroleum assets, right? That's really what it is. Think Harry Markowitz here with petroleum portfolios. So if I click on Nigeria, first of all, that was 1,000 Monte Carlo trials, and the green dot says, here is your risk, and here's your return. The return is the average profit. The risk is like the root mean squared loss. Oh, what's this picture? The blue dots are within budget. The yellow dots are beyond budget. Notice if I increase the budget, this blue line goes up. Now, Control Z, I bring it back. This brings about an extremely important concept that people do not pay enough attention to. Models need to be interactive. I call this limbic analytics. You've got to get the user's limbic system involved. One of the examples I use is, what PowerPoint did you use to learn how to ride a bicycle? Oh, you're too old for that. Oh, you used a book to learn how to ride a bicycle. Which book did you use? Because I have a friend who wants to learn how to ride a bicycle, and I haven't found a book that's worked so far. Of course, a book isn't going to work because a book doesn't activate your limbic system. Now, the stuff we're doing with uncertainty here involves both the seat of the pants and the seat of the intellect, right? Kahneman called those System 1 and System 2. You can do better than that. Seat of the pants and seat of the intellect, and connecting them is what I call limbic analytics. So I have this risk return space. Oh, here is my histogram. And we see a little red lump on the end. Here, let me double down on Nigeria. Again, the highest average, click, and a bigger lump. Yeah, this is, oh my gosh, look how risky we are. The blue line is the Pareto optimal curve called the efficient frontier by Harry Markowitz, right? And so this is risk, this is return. Anything to the northwest of the efficient frontier is impossible. This, in fact, is how they caught the fraudster Bernie Madoff with stock portfolios that couldn't exist. Okay? Anything on the frontier is rational, and where you go depends on your risk attitude. Anything to the right of the frontier is just plain nuts. Who wants more risk and less return? It doesn't make sense. Okay. Anyway, I've done this, and we see that, unfortunately, Nigeria has some political risk. And by the way, I'm afraid you could replace Nigeria with Russia these days, right? Very similar thing happened. In our version of the model, Nigeria sent gas to Europe through a big pipeline. In reality, Nigeria is an oil play. Forget that. Imagine then it's even closer to Russia. That Europe is getting a lot of gas through Nigeria. And so it turns out, let me undo these. It turns out that Norway also supplies gas to Europe. Let's see what Norway looks like. Oh, Norway's very bad. Look, yeah, low risk, low return, but not the one you want. Oh, look at that. 28.27 is versus the average profit versus 55.92. Well, why is that? Well, it's because the Norwegians want us to subsidize healthcare and education and junk like that. Who needs that? They take $10 off the top of every barrel. So we don't like Norway. Oh, but what if Nigeria blew up politically? Oh my gosh, the price of gas would go up in Norway. So now I'm going to look at the slurp. Over here, I have these global economic and political factors. And so, for example, down here, that one was a trial on which Nigeria blew up politically. And if we look at the region 1 gas price, think Europe, you can see it's about $20, some kind of distribution. Oh my gosh, but if Nigeria blows up, it's 46. It doubles. And by the way, that's Econometrics 101. It wouldn't take you long to figure that out. Oh, now let's look at the ventures over here. That is, these two are the two Nigerians. We're now losing 230 million bucks. And look, Norway, which I told you was a dog. Oh, it's a gold mine when the price of gas doubles, right? 598. And how do we see this? How do we engage our limbic systems in this? Now remember, this is the SLURP, Stochastic Library Unit with relationships preserved, because each of these global factors, which are going to show up in SimDec in a second, okay, they're going to play a role. So I take Nigeria, and then if I'm looking at this blindly, I said, well, Alaska isn't correlated to Nigeria. Let's take Alaska, Alaska in, Alaska out. Okay, that it's like an oil play instead of a gas play. So my return's going up, my risk isn't going back and forth. Oh, what about Norway? Norway in. Oh my gosh, Norway out. Wait a minute. The risk goes down, the return goes up. Yes, boys and girls, that's called a hedge. In the event that Nigeria blows up, Norway comes in and rescues the day. Okay, but why click around like this when I can click on the efficient frontier? Click. So, oh, well, there's venture one, venture two, Nigeria, Norway. And if I want to take more risk, I click up here, click. Oh, it's got two Norways. Okay. Sorry, two Nigerias. Norway hedges it. Then you got Alaska. So I see SimDec. I do not recall the moment of falling in love with this thing, but it was very short. I'm now going to take you. Oh, and let me tell you, so much here in explaining this stuff has to do with maintaining credibility and not scaring your audience. Okay? I have to say something else bombastic about the chance age. We have redefined the term probability distribution. How can you do that? I thought the Bernoullis did that 300, 400 years ago. No, no, no. It has a new definition. Probability distribution is now a 9-syllable term that triggers post-traumatic statistics disorder, or PTSD. Don't use that term when you can use the single syllable chance. If you want me to prove it, want me to take 20 minutes, a probability distribution is just the chance that the number you're worried about is less than any x. That's all it is. Okay. So the problem with this was, how would I know the chance that Nigeria is going to blow up? I wouldn't. And anyone who told you that should be promptly kicked out of your office. Now, this was back like in 2005. Oh my gosh. Excel now has got something more powerful than the data table. Excel has something more powerful than the data table. It now has something called dynamic arrays. And I'm going to show you a little more about them in a minute, because ironically, a day or two before you last contacted me, I had used SimDec in anger for the first time. Yeah, that in anger means like as a weapon of knowledge. And it is now my favorite example of SimDec, but I'm going to start with this one, which I love. Now, this is the shell model using the dynamic arrays in Excel, which are incredibly fast but very difficult to use usually. But the chance of disruption is a variable. And so now here let me notice where we are. We're on the efficient frontier if the probability of disruption is 0. Well, we thought it was maybe 15%. So let me plug in 15% here just as a starting point. And when I hit the enter key, it just ran 1,000 trials times each of 300 portfolios. That was 300,000 simulations, right? 300,000 moving parts. Oh, and look at what is this over here? Oh, here, let me reduce this to 8%. What you're looking at here, oh, and we refer to this as the galaxy. So this is like the galaxy of all possible portfolios. Every dot is a portfolio, right? Not a project. And we see parts of the galaxy being rent asunder by probabilistic forces. Let's crank this back up to 15%. And what are these? Oh, these are what I'm going to call the naked Nigerian holdings. You got both Nigerias, but you do not have them hedged with Norway. Okay, well, God, that's not efficient. Let's click over here. What's this one over here? Click. Oh, just a sec. I got to reset the graph. Okay, now I'm on the efficient frontier. Oh, this looks like SimDec. So I had developed a name that it was a wonderful name, but it didn't really apply to anything until I saw SimDec. I had the name schizogram, which I had applied in a different setting to not all the bars are really equal. But a schizogram is a perfect name for a histogram with multiple personalities. And we see them all together, and you see this distribution, and you put it down on the psychiatrist's couch, and you say, tell me a little about yourself. It says, well, these are all my Nigerian investments. And you can see when Nigeria blows up, something bad happens over here. Oh, the green ones are my Norwegian investments. And you can see that unlike having a downside of Nigeria, Norway's got this big long tail on the top because the price of gas is going to be uncertain when Nigeria blows up, but it's going to be big. Trust me, it's going to be big. Okay, good. And that, oh yeah, wonderful. Okay, now let me point something else out here. There's the person, always the person who does not believe in probability. The numbers are uncertain. How could you, you know, you're going to give me the wrong probability. No, give me a number. And what you do is now you take the flat dice. You apply this to their nose and you rub vigorously. People love these things. Okay, so that person gets up and says, you're just blowing smoke. If there were it's a 15% chance which you pulled out of your butt. Look, if that were a 20% chance, it would be a completely different portfolio. See? Oh, it wasn't. Wait a minute. Well, yeah, but how about a 5% chance? Oh, wait a minute. How about a 30% chance? And look at our little schizogram over here doing its little thing, its little schizophrenic dance. Every time I do anything, 300,000 moving parts, limbic analytics, if you ever saw it, okay? And finally they say, well, yeah, but what if it's 0? No one thinks it's 0. Are you kidding me? So now here's what we do. And this now is a chance age presentation rather than a stochastic modeling presentation. It's the board of directors of the oil company and the operations research analyst, the probabilistic stochastic modeling guy comes in and says, hey, today, ladies and gentlemen, we have to determine the probability of Nigeria blowing up so we can pick an efficient portfolio of exploration ventures, right? And no one has any idea what that is, and they form a committee and they meet every 6 months for 5 years, and Nigeria blows up under their noses 4 times. Let me tell you the other approach. Chance man gets up, does this a little bit. Yeah, what if it's 25%? Yeah, sure. And then, Chance man says, okay, ladies and gentlemen of the board, do we hedge Nigeria with Norway? Up or down vote? It's very compelling. This is what I have in the afterword of the book. And this blows me away. And this is so useful. But it's just the beginning. Here is where I had a real adventure just the other day. Now I'm going to say something about dynamic arrays. The data table you can look up. And we have a wonderful tool called ChanceCalc. I hope you have a link to the ChanceCalc video. The models you saw, not that SimDec one for shell, although it'll be easy to automate SimDec with SIPmath. But our typical models, you build them like the first shell model, and you build them with our add-in tool, but then the tool is not required to run the add-ins. Oh, I did the dice, something like that. It builds the data table for you. And you must be a little careful, because if you have a bunch of variables, and suppose variable 3 is a normal distribution whose mean is the average of variable 2, it's not going to work. You are in effect getting a circular reference through the data table. You won't even know it. The answers are garbage. Okay. And what I've discovered is that you can couple the dynamic arrays to the data table. And it took SimDec to validate that it worked correctly. And it was very exciting. And it's a beautiful, beautiful thing. So let me start out with, what is a dynamic array? They've been around for, 4 years, 5 years in Excel. There's 10, and there's 2, and now I type equal rand array. And mind you, I'm doing everything in Excel because a billion people use Excel. All of our standards are cross-platform, Python, R, you name it. And in fact, if we go down to back to the probability power grid, the power plants are probably mostly written in Python, but who knows what AI is doing? You can't even reverse engineer that. But hey, if you don't trust it, wait a week. It's getting smarter a lot faster than we are. Okay, so rand array 10, 2. And I hit the enter key. Oh, so this is, it's an array. It's only one formula. Oh my gosh. What if I made that 3? Oh, 3 columns. What if I made that 1,000,000? 1, 2, 3, 4, 5, 6. Boom. Oh, that was fast. Let's press the F9 key. Oh, 3 million, 3 million, 3 million. That's pretty fast. Okay. Now, here's another nice formula. Let's put this back down to 10. Boom. Now my formula is equals sequence of that 1 through 10. Right? 1 to 1,000,000. The sequence command can be used as a Monte Carlo counter. And now I take you to, if any of you have heard of Doug Hubbard, he has built a wonderful seedable random number generator for Excel. And it's in there. And it's so big, it doesn't fit in a cell. Okay, I mean, it does fit in a cell, but it doesn't fit on one line, right? In fact, it's beautiful that it fits in a cell. And it actually has 4 separate seeds. So there's 3 of them. You know, there's 1,000 of them. And what's going on here is that one of the seeds is pointing to the counter, and another seed is pointing to this thing. So let me say this is the individual seed, this seed over here. I change that to 5, and I get another sequence. All right? Now, one of the things that happens in simulating risk is that you get a random number of risk events. It might be a Poisson number of explosions on a pipeline network. And every risk has an IID, identical distribution, independent, of some kind of loss. Well, that means, let's think of this number as the number of events. If I had 3 events, I get 3 losses. This, by the way, is just a uniform over here for purposes of demonstration. But that number up there could be a Poisson variable, and maybe sometimes it's 7, and whatever it is, I then can sum these at the bottom. Sum them up, and then I said to myself, what if I make this seed the seed through a data table? So I'm taking the dynamic array and running it in the middle of a data table. I said, what could happen? Number 1, I could hang Excel. Number 2, I could blow all the circuit breakers in our house. Number 3, I could ignite the atmosphere. I didn't know what was going to happen. It's Excel. Excel isn't like math. Excel is like physics. And I've had some pretty bad things happen. It did not ignite the atmosphere because we're having the conversation. It didn't even blow the circuit breakers in my house. In fact, it didn't crash Excel. The question is, what did it do? And it took SimDec to find out. So what I've done here, we got to post a version of this. I got a blog about this. But here's a number. I'm going to pick a random number of uniforms. A uniform is a spinner. First, I pick a number, an integer between 1 and 4. In this case, it was 4. Let's look at a different trial. This time it was 1. Then the dynamic array sums up. Let's go to the next trial. Back to 4. The dynamic array sums up, and here's the notation. The sum of D5 pound. And by the way, some years ago, Microsoft bought a version of R called Revo Analytics. And apparently they left R and Excel in a room overnight. And something exciting happened. I think this is like the offspring of R and Excel we're looking at here. But who knows what's going to happen if you do all this stuff and then run this back through the data table, okay? So, well, that's the distribution, whatever the heck that means, right? Look, what's going on in here? So, what on earth would the distribution of the sum of a uniform integer number of uniforms look like? That takes us to, now we have SimDec telling us what's going on. We generate a random uniform. Here. Where did that shape come from? Again, we didn't ignite the atmosphere, but that didn't mean that the numbers we were getting were at all right. You can do things with Excel that internally break Excel and you never know it, like running things through the data table twice. And I get this, I say, well, what the hell? It's got a distribution of something. How do I prove that I'm getting the sum of an integer number of uniforms? And I thought a little, oh my God, SimDec. And so, let me explain what's going on. We ran 10,000 trials. And on those trials, and here's how I've partitioned, right? Here's how I've partitioned my trials. If n was 1, oh, look at that, I get a uniform. If n was 2, I get a triangular like the dice. If n is 3, it starts getting bell-shaped. If n is 4, it's more bell-shaped. Oh, and look how they stack up. So n equals 1 is that little blue guy down there, uniform. If n equals 2, now remember, n equals 2, but now we're choosing uniform between 1 and 2 and adding 2 uniforms together. Well, when it's 1, you still get that guy, but when it's 2, you get your triangle, but now the triangle's stacked up on top of the uniform. Holy Toledo. And then here's 3. And if you get these low numbers, it could be 1, 2, or 3. Oh, and look at this big spike here. Well, that's because this spike occurs when it happens to be 3. Okay, now I do have, let's look at this with 100,000 trials. So the important story here is that I did research that required SimDec for me to know that this crazy way to tie dynamic arrays and data tables into the same model works. This is the right distribution of the 100,000 trials. And it's because you look at something like this, you say, well, what could that be? Well, what that is if you get a 1 or a 2, you're up to there. The biggest number you can get is 2. As you know, you have one chance. There are 4 numbers, right? 1, 2, 3, 4. You have one chance in 4. You have one chance in 2 of getting a 3 or 4. And as soon as you do that, you get this big spike here, right? Okay, so no, you wouldn't understand it, but you look at that and you say, Sam's telling me it works. That looks like it's working. I don't know what it's doing. I know he didn't ignite the atmosphere because we're all still here. So I need to write this up. It needs to become a part of SimDec lore. But I was so thrilled, and this happened. I think might as well show you how easy it was to do. How easy SimDec is to do with SIPmath.
Go ahead.
So what you're going to do is have multiple output cells, one for each of the personalities in your schizogram, right? Because I mean, that's typically what we want. Oh, we had a gasket failure, you know. What happened when you had a gasket failure? Oh, the chemical vat overheated. I don't know what you're simulating, and I don't care. But you're dividing it up into, what do you call them? Events, or what do you call the things you're partitioning it up into?
States of variables. Here you have 1, 2, 3, 4. Yes. Or
Great.
if you have several variables combined, you can call them scenarios.
And it doesn't matter what you call them because this is what it is. Right, like here's the scenario. You know, the scenario that you roll, you get a 1 is just the blue one. The scenario you get a 2 remember, you never get a 2 by itself. You've already got the 1, then you add the 2, right? You have to add them together. And then that's the triangle. And okay, anyway, so what we do is this. Our output cells appear, this is 100,000 trials, mind you. And what I do is make sure that output 1 only appears when n is equal to 1. Otherwise, now it says NA, which is confusing because Excel has an NA formula. It's not that. I go to the output cell. And I say, this is for n equal 1. So if this thing equals 1, then count it. Otherwise, quote NA. But I could just as well do quote junk. Now, you'll have to hold on a minute because it is going to do 100,000 trials. I should have done it on this earlier version. There we are. And now, when I look at the PM table, it says junk. Just any string that says this is not a Monte Carlo trial, so ignore it, right? You do all that. And by the way, I've said count. So N1 is now the name of the range over here. 100,000 things that either say junk in it or have a sample from a single uniform, right? N2 either has NA in it or it has the sum of 2 uniforms, right? And here I take the count and divide by, oh, that's 10,000. It now should be 100,000 because what I'm getting is 25% chance of each because that number was uniform. We're getting to the weeds now, but I've got to find the time and resources to write this up. And that is just like, that says a bunch to me. It has opened up a whole new path for me to go down with Excel and ways to test that it's working, right? So anyway, that's it from SIPmath. Good to see you guys.
Good to see you. Thank you, Sam, so much.
I'll send you these models too.
Yes, perfect. Thank you.
Bye-bye.
Bye-bye.